Hello there, welcome back to another video. Today we're going to be doing related rates. Now related rates are actually really similar to implicit differentiation. In fact, it's the exact same formula, but now we're just dealing with different variables. So instead of y, we would have maybe volume. Instead of x, we definitely have t. So let's get into it. Before we start with anything, we need to define what a rate is. Now, things that are rates could be speed, that's the type of rate. There's rate of reaction in chemistry. There's population growth rate. All of these are rates. And what do they have in common? Well, let's see. Speed is distance over time. Rate of reaction is reactions over time. And population growth rate is population added divided by time. So as you can see, what they all have in common is that they're being divided by time. That's what a rate is. A rate is basically the change of a variable across time. So that's what related rates are. And today we're going to be talking about a couple ways that they can apply to some of the equations we've learned in middle school. To best understand this, let's do a practice problem. So what does our practice problem say? Our practice problem says that a spherical balloon is being inflated at a constant rate of 100 centimeters cubed per second. Determine how fast the radius of the balloon is increasing when its radius is 10 centimeters. Okay, so before we do anything, we need to understand what exactly is going on in this situation. So we have a balloon and it's a sphere. So this right here will be our drawing. And our radius is at the point where the radius is 10 centimeters. At the point where the radius is 10 centimeters, the balloon is still expanding at a rate of 100 centimeters cubed per second, which means its volume is still increasing, right? And that means its radius will also increase. But we're trying to figure out how quickly its radius will increase. So the whole balloon will be expanding at a rate of 100 centimeters cubed per second. And we need to find how quickly the radius itself is moving outwards. So if that's not clear right now, I'm sure it will be by the time we're done with this question. So the first thing we want to do in this question is we want to figure out what we're given. So what is the information the question gives us? Well, it says a spherical balloon is being inflated at a constant rate of 100 centimeters cubed per second. So a rate, and over here what's being changed is the volume, right? Because this is centimeters cubed, and anything cubed, any measurement of length cubed is a measurement of volume. So we have some sort of measurement of volume over time, because this is a rate, is equal to 100 centimeters cubed per second. And then that's the first thing. And the second thing then is determine how fast the radius of the balloon is increasing when its radius is 10 centimeters. So that's our second thing. Radius is equal to 10 centimeters. Great, now we know what we're given. Let's try to see what we're trying to find. And what we're trying to find here is over here. Determine how fast the radius of the balloon is increasing. So how fast something is increasing is its rate, right? So we can say we're trying to find the radius over time, right? So we're trying to find how quickly the radius is increasing. And now what kind of equation will we use here? Well, we know there's a volume involved, we know there's radius involved, and we know it's a spherical balloon, right? So there's only one equation for volume and radius and for a sphere, and that is volume is equal to 4 over 3 pi r cubed. That's our equation for volume. Great, that's it. That's the entire setup for this problem, and now it's going to be easy from here. Okay, and since we're talking about a related rate problem, we need to take its derivative, but not like dy over dx. No, we're not doing dy over dx. We're taking the entire thing, we're taking the derivative of this entire thing, and the notation for this can be written as d over dt with respect to time. What that basically means is it sounds complicated saying with respect to time, but it's actually really simple. All it is just finding the rate, right? How quickly it changes, we need to divide it by time, like any other rate that we've talked about before. We need to take the derivative with respect to time. We need to divide by time. So, okay, You may think the process is different, but it's actually really pretty much the same. So let's start with v. The derivative of v, we're just going to use power rule. So we take the 1, bring it forward, so it'll be 1 times v to the power of 0. So that would be 1, but, and this is where implicit differentiation comes, right? Volume is a function of time, right? Volume is a variable here. So it's similar to how y is in something like y squared is equal to x squared plus x. We need to take its inner function as well. We need to take its derivative of the inner function as well. So we need to apply chain rule. And the inner function over here is not v prime, but it's dv over dt. Now, if you notice, dv over dt is similar to this given right here, v over t. So what we've just done is we found the rate of change of the volume. Okay, now let's finish off the rest of the question. So we did the left-hand side, so we got dv over dt is equal to 4 over 3 pi. Now this is a coefficient of r cubed, right? So we don't need to worry about this. We only need to worry about differentiating r cubed. So r is another variable, which is not t, right? So that means we're going to have to use implicit differentiation on r as well. So we take power rule on r, so we get 3r squared, and then we need to multiply that by the derivative of r with respect to time. So dr over dt, that's just chain rule, which we learned in the last video. So then we get the equation dv over dt is equal to 4 over 3 pi times 3r squared dr over dt. Okay, so let's quickly contextualize what exactly we have here. This is the rate of change of the volume, right? Then this is the radius, the current radius, and this is the rate of change of the radius. So if you notice, this is what we're trying to find. We're trying to find radius over time. We're trying to find how quickly the radius is changing, right? So right here, dr over dt is radius over time, right? Remember, d just means a very small quantity of. So a very small quantity of r divided by a very small quantity of t will give us the rate of change of r and t. So, okay. Now we can also simplify this a little bit. We can cancel out the 3's here, right? So then we're left with dv over dt is equal to 4 pi r squared dr over dt. Perfect. This is much easier. Now, since we're trying to find dr over dt, we can isolate dr over dt here. So we get 1 over 4 pi r squared dv over dt is equal to dr over dt. Now this is basically it. Now all we have to do is just plug in our variables that were given to us, right? If we look at this, we have one given, which is the dv over dt, and another given, which is the r. So we can plug these in. In the given, it says the dv over dt, or v over t, the rate of change of volume is 100, and the radius is 10. And they're both in centimeters. Be careful of the units. Otherwise, you'll have to convert. Make sure all of these units are the same. Let's plug our givens in. So we get 1 over 4 pi times 10 squared times, and then the rate of change of our volume is 100 centimeters cubed per second is equal to dr over dt. And then we can open this up a little bit. So we get 1 over 4 pi times 100 is equal to dr over dt. And then if you notice, we have 100 in the numerator and 100 in the denominator, so we can cancel them out. So then we're left with dr over dt is equal to 1 over 4 pi. And that right there is a constant, which means we're done. We found our answer. And just be careful, the unit for this is centimeters per second, because we want to look at this here, right? We got r divided by t. So radius is measured in centimeters divided by what's measured in time, seconds. So that right there is our final answer. It basically means that as I increase the volume of my balloon by 100 centimeters cubed per second in every direction, my radius will increase by 1 over 4 pi centimeters per second. So that's basically it for this video. This is just an introduction into the theory behind related rates. But this can apply for many different formulas. For example, it can apply for pi r squared, the area of a circle. This can apply for the area of a rectangle, length times breadth. This could apply for the volume of a cube, side cubed. This could apply for a cone, 1 over 3 pi r squared h. This could apply for a cylinder, pi r squared h. And this can also apply for other problems like displacement, velocity, and acceleration. So that's kinematics, and that's one thing we go into in the next video. And then there's also applications into other types of movement. So for example, there's a question where I have a wall, I have a ladder on the wall, and let's say my ladder is falling this way. What's the rate at which it falls the other way? So there's multiple different questions here, and I think next video we'll go through some of the related rate questions, and they're tons of fun. But I think that is it for this video, and I hope this has made related rates a little bit less intimidating for you. And yeah, I'll see you in the next one. Bye-bye.